We're now in a position to consider the scramjet as a whole in more detail. Look at the diagram illustrated below, which shows the various parts. The function of the intake is to scoop up air and to compress it. This is done by carefully designing it to utilize shock waves. As an example, consider the simple intake shown below, which uses a single shock wave. As we learned from our previous videos, the flow will slow down as it crosses this, and the pressure will rise. However, a single shock wave is not efficient and doesn't give enough of a pressure rise, so more are generally required. A logical conclusion of this is to generate an effectively infinite number of very weak shock waves utilizing a continuously curving surface. The shocks here are so weak that the process is isentropic, and this is called an isentropic compression surface. After the intake is often a length of duct called an isolator, which is designed so that the conditions at the inlet don't affect the combustor, and vice versa. The mixing and combustion section is next. I don't intend to say much about this here, as we'll study it in a little more detail later. However, fuel is sprayed into the stream from a wall-mounted injector or wall-mounted injectors and then ignited. This liberates the energy which we are going to use to provide thrust. Finally, we have a nozzle. This is perhaps the part of a process best understood because it works on exactly the same principles as a jet or rocket nozzle, and is a diverging duct which accelerates the flow. The only real difference being that the flow, already being supersonic, doesn't need a throat section, actually making the process simpler than in a jet or a rocket. Expansion can often be considered isentropically as well. The cycle thus produced conforms approximately to a Brayton cycle as shown in the graph below. In this graph we can see the compression surface, and in the perfect Brayton cycle this would be an isentropic process. The combustion process, which occurs at constant pressure. This is because both sides of a combustor are open, as we explained in an earlier video. And finally, the expansion, which is also ideally an isentropic system. You can use this diagram to calculate various important things about the cycle. For example, the work done and its losses and its efficiencies, using normal methods which you can find elsewhere online. In the following videos, I will review the intake and the exhaust processes briefly, but concentrate on the mixing and burning process. This emphasis is for two reasons. Firstly, the intake and exhaust processes are very well covered on YouTube videos elsewhere. And secondly, it is the mixing and burning issues which are considered the roadblock to getting a practical scramjet to work properly.